This is Lab 1 for Physics 2211, going over constant velocity. Now, in this experiment, we will be observing a foam ball moving across a table with a constant velocity, and we will calculate the velocity by comparing position over time for an experimental and computational model. A couple things to note before we begin. The first being Newton's first law, which states that an object in motion stays in motion with the same speed and direction unless acted upon by some net force. The second law implies that a change in momentum means that there is an acting net force. So what we can gather is that the net force acting on an object is zero, and when this happens, constant velocity is then achieved. What we can take from the second law is something called the velocity update formula, which calculates a final velocity given an initial velocity, a net force, mass, and change in time. And when the net force in this formula is set to zero, the resulting formula is then final velocity equals initial velocity. This is the tracker video that extracts data from the ball moving across the table. Now, as you can see in the top right graph, the very linear resulting function shows us that we should have a constant velocity. The data from this bottom right-hand table was then extracted and compared to a computational model based on the same scenario. Now, it is important to note that there are a couple things that may lead to skewing results with the experiment. One being the distance not being properly calibrated for the table, a changing in y values as shown in the second chart over here on the right can give some skewed data. Clicking the exact same spot on the ball as it moves also has an impact, as well as the frame rate of the video. All of these are factors that are very hard to control and could have a compounding impact on the resulting data. This is an excerpt from the computational model that is used to predict the position over time function. In this little snippet, we add some initial conditions to set to the ball. For instance, the position being 0 as set in the experiment axis, and then the velocity being 0.61, which was taken from the final position and time, comparing it to the initial position and time. And because the experiment had such a linear slope, then it should be safe to use the overall average velocity as opposed to using more initial velocities. Now in this, the ball mass is set to 1, but it ultimately does not matter, as when you have a zero net force, placing 0 over any mass ends up simplifying down to 0 anyways. This part of the computational model is the actual calculation loop that updates the velocity and position over time. Now, it does technically update the velocity over every iteration, but it does not actually change, given that it should be constant. So it adds a 0 vector to the current velocity vector. The left graph here shows position over time from the computational model. Now, given that it has a very linear slope and very constant slope, it can be taken that it has a constant velocity, as velocity is associated with the slope of position over time. On the right, the velocity versus time shows us that it's constant velocity, since the velocity here is not changing and stays a consistent 0.61 meters per second. On the left, you have the graph for the experimental data, and on the right is the computational data. And when you place these two graphs on top of each other, you can see that the results are very similar, with a little bit of skew in the experimental data. Now, while the data stays very close to each other, there would likely be more drastic deviations over long time intervals as opposed to the 1.6 seconds used in the experiment. This is because there may be multiple unknown variables impacting the experimental data, such as rolling on a potentially uneven surface, or frame rate in the video, etc., etc. Now, what if the axes in this experiment were flipped? If the axes were flipped, the absolute value of the distance traveled over time would remain the same, with velocity only changing its direction. The representation on a graph would simply flip into the negative direction like it does here on the bottom right. Now, note that the time doesn't actually change into the negative direction, given that it is an independent variable here. It is actually very difficult to determine exactly how many forces are being added up to give a zero net force. Friction, gravity, and air resistance are all likely contributing factors, but there may be many more that we don't know about in the particular scenario. Additionally, identifying how much of a contribution each force has is also very difficult. For instance, friction might be a very significant factor, or it could be very minuscule. Thank you.